Hi there, grade 11s, and welcome to today's lesson for physical sciences. Today we're going to be covering intermolecular forces. So hopefully you are ready for this. You've got some background to that. If not, don't worry, we'll catch you up, we'll keep you up to speed. So let's have a look at the first thing that we do, and what do we always start with? Terminology. So let's see what I've got for you today. What do the following words or terms mean? So I'm going to give the words or terms to you, and you are then going to have some time to write down what you think they mean, and then we will go through them together. So what do the following words or terms mean? First one, intermolecular forces. The next one, intramolecular forces, or intraatomic forces. Melting point and boiling point. So I just want to draw your attention to intermolecular and interatomic. Okay, don't get them confused and think they are the same thing. So 4 words or terms that I'd like you to write definitions for. I'm going to give you 2 minutes starting now. Okay, everybody, your 2 minutes are up. Let's see what you've got for me. Compare your answers with mine. So we'll start with intermolecular forces. These are electrostatic forces of attraction or repulsion which act between neighboring particles. Now, I just want to draw your attention here where it says particles, we are meaning molecules, and sometimes we mean ions. Okay, so we're not speaking about atoms specifically here, we're talking about molecules or ions. And the second one, interatomic. Now, some of you must have noticed that I used a different terminology when I first read this out to you, and I said intramolecular. Now, that is just another terminology for the same thing. These are forces that hold atoms together. Really fancy term for ionic bonding and covalent bonding. So when you hear us talk about intramolecular or interatomic, we are talking about covalent and ionic bonding. Now, why is it important that we differentiate or we draw a line between intermolecular and interatomic? because intermolecular is how the whole molecule behaves. Interatomic is what happens inside the molecule. Okay, and that is important to remember. Moving on. Melting point. What is that? It is the temperature at which a given solid will melt. When we say given solid, we mean any solid. So if I say to you, what temperature does ice melt at? You can tell me for ice. If I ask you what temperature carbon melts at, you can then give me that temperature. So it's a specific temperature for any substance. Then lastly, boiling point. This is now the temperature at which a liquid boils and turns to vapor. Same concept applies here. This is any liquid, okay? So we will know that water boils at 100 degrees Celsius, but that does not mean that everything boils at 100. You get some substances like oxygen. Oxygen boils below zero, like minus 200 or 223 if I remember correctly. That's where it boils. Boiling just means to change phase, to go from a liquid into a gas. The one we're most used to is water, and that's why we always think 100 degrees, because that is the temperature at which water will then turn into a gas. Okay, so remember, with melting point and with boiling point, with both of those, they are specific to the substance. Right, let's move on. So I said to you that today we're going to be talking about intermolecular forces. And those being, because we've just done the term, the forces that occur between molecules. So there are several types of intermolecular forces. They range in strength from very weak to very strong. And the forces depend on how many electrons are distributed within the molecule. So in other words, how many electrons are in the valence levels. Okay, so we're talking valence here. So how many electrons are in the valence levels that surround the atoms? Now, some of you must be asking the question, why do we need to know this? The reason that we need to know about intermolecular forces, in fact, there are several reasons, but right now the most important one is it's going to explain to us and help us to understand why substances behave the way they do. Why does water boil at 100 degrees Celsius? Why does it melt or freeze at 0 degrees Celsius? Why are some substances at what we call room temperature, so 20 degrees, 22, 25 degrees, whatever the temperature is in your room at the moment, why are they still gases? And why are some substances still solids at that temperature? So intermolecular forces, the forces that are between the two molecules, or millions of molecules, they will explain or they contribute to the behavior of the molecules, how they behave, how they interact with each other. And that is the purpose for us learning them. Because once we know how molecules behave with each other, when we move on to our next sections where we talk about reactions or speeding up reactions or slowing them down, because we know how the molecules behave, we're able to make better judgments and give better answers in terms of how we understand how the reactions are occurring. Okay, so this is a really important section. Need you to pay attention, need you to be thinking. Any questions that you have, remember, jot them down, ask a friend, ask your teacher, look it up in the textbook. Google it if you need to. Ask somebody who's been through grade 11 and has got the answers for you. Okay, so not sure, remember, make a note and ask. But let's get back to what I've got for you. Okay, there are 6 intermolecular forces that we're going to be talking about. But I want to draw your attention to intramolecular. I just want to talk about the bonding first. Remember, I said to you that it is important that we distinguish between forces and bonding. So the question is, why do we have to distinguish between the two? And the answer for you is that bonding, so what happens inside the molecule, affects the outside of the molecule. So in other words, bonding will have an effect on the intermolecular force. Okay, so the type of bond is going to affect the intermolecular force. So we've got 3 bonds that are illustrated or represented in front of us on the board. A and B are the same. Oh, goodness, that's a terrible, terrible line. This is why I do science, because my drawing, I'm afraid, would make artists cry. So let's try again. There we go. Those 2, A and B, are the same type of bond. It tells us here they are covalent bonds. Okay. Covalent bonds mean usually that they occur between 2 nonmetals, and it is the sharing. Okay, remember, it's the sharing of electrons. And what is important in these type of bonds is our electronegativity. Now, I didn't give you that as a terminology because I know you've just spoken about it in your previous section, okay? But in case you can't remember, electronegativity is the attraction that one atom has for a shared pair of electrons. Okay, so what does that mean? Let's look with this molecule up here. Chlorine and chlorine, that there would have been the 1 chlorine atom, and this one here, the 2nd chlorine atom. And in the middle, between the 2 is where the 2 electrons should be shared. So if I take away the lines that I've drawn, you will see that's exactly what's happened. We've got the 1 atom over there, and then we've got the 2nd atom beginning and ending over there. So it looks like it's joined into one whole atom. What's actually happening is that the electrons, they come together in what we call a cloud. Okay, so they come together in what we call an electron cloud. That does not mean that there's millions of electrons and they're trying to get together and make rain. That's not what it means at all. Because the electrons are so small and it's hard to try and figure out where they really are at this moment in time. Right now, where's the electron? It's not possible to do that. But they go so fast and they're so small, their behavior and their movement makes it look like there's cloud around the atom. Well, that's how scientists are picturing it at the moment. Okay, so you'll see that the gray here is representing an atom. If you look at the board again, the gray represents an atom, and I've got the dotted line to show where the 2 should be meeting. And what they've done is they've drawn in our pairs of electrons, but that gray actually fills up space, and it indicates that that's where the electrons could possibly be. Anywhere in there we can find an electron, and anywhere in there we can find an electron. Okay, so that is why the space filling diagrams are often used, just to show you that there's any possibility of where we can find these electrons. What we've done in this diagram, however, is we've shown nicely and neatly, that's not what I wanted to raise this picture here. There we go. We've shown you neatly that we've got electron pairs. So now remember, if the 2 electrons come from the same atom, they are called lone pairs. So there's 1, 2, 3 lone pairs, and 1, 2, 3 lone pairs for the other one. And in the middle, here, put a dotted line around it, that there is our shared pair. Okay, so now I've been talking on about space filling and all sorts of things. Why am I telling you about this? Because we started off by saying we need to know what electronegativity is and that bonding affects intermolecular forces. These 2 atoms, chlorine and chlorine, they're the same. They're identical. So they've both got 3 lone pairs of electrons and they are sharing 1 pair of electrons. So there is no way that they are going to have a pull of electrons to one side or the other. And hence, this was called a non-polar covalent bond. The bonding electrons are shared equally. Okay? Now, if you look a little bit further down here, let's just do that. I've got some space. Look at our H and our Cl. Again, here's our space filling diagram, and you see you've got the red and the blue, and that's showing us the possibility of finding the electrons. Now, chlorine has got 3 lone pairs, Okay? Hydrogen's got no lone pairs. All it's got is its one little proton, and then it's got its shared pair of electrons. Now, if we look on our periodic table, our substances will show that chlorine has got a greater electronegativity than hydrogen. So that means that chlorine wants to attract the pair of electrons closer to itself, meaning that there's more of a negative, and that's why we've got this sign here, on the right-hand side, and less negative, which will make it positive, on the left. Okay. Guys, we're going to go for a break. I'll come back and talk about the ionic bond. We've done a lot of work this session. Well done. Have a break. See you soon. Welcome back from your break, everyone. I know we did a lot of terminology. I hit you with a lot of stuff before the break, but I know grade 11s that you guys are working hard and that you're trying to keep up with what's going on. So well done. Keep it up. We've got a few more things to do in this section before we introduce the new stuff. So just bear with me, a little bit more revision. Let's get stuck in. Okay, so we're going to talk about the ionic bond now. So again, just to recap, we were talking about electronegativity difference. Okay, here the difference in electronegativity between the two atoms is so great that the electron literally moves from one to the other. So we now have got on one atom a full set of valence electrons, and on the other atom it is completely empty. Okay, so it's lost all of its valence electrons. So hence, it is called an ionic bond because, as you can see here, it's Na plus and Cl minus. It is two ions that are joining together, that are being attracted to each other. So go back to what I was saying just before the break. Bonding affects the intermolecular forces. You can see all of the lone pairs of electrons that we've got. You can see how with the polar covalent bond, one side is slightly more negative, one side of the bond is slightly more positive. With ionic bonds, you've got one side of the molecule, or one side of the compound, should I say, is positive, and the other side of the compound is negative. So these factors affect how the substances behave with each other. Now, let's talk about the different types of bonds that we have. Okay, remember I said to you there were 6. Okay, sometimes they're known as van der Waals forces. Okay, so if you do come across, there was a Dutch physicist who spent a lot of time researching this, and in honor of the work that he did, these forces were named after him because he discovered and described them. So the first few, a dipole-dipole. This is a natural attraction between opposite poles of polar molecules, and this is the key here. Okay, so if I was to draw, and I'm going to draw it badly, but I'm going to try, I'm going to draw that it was the H and the Cl from the previous slide. And we said that this was slightly positive and this one is slightly negative. Okay, this here is termed a dipole. Okay, di meaning two and then poles. Okay, so a compound that is polar is also known as a dipole. So when we have a dipole-dipole interaction, it means that it's polar molecules that are interacting. Okay, so make a note of that, please. The second one is an ion dipole. So this is an attraction between ionic substances and polar substances. Okay, so this one is fairly straightforward. Ionic substances and polar substances. And a really nice example here is if you dissolve salt in water. Salt being NaCl or sodium chloride and water being H2O. So here we've got ionic compound and, oh, the I is missing, ionic compound. And over here we have a polar covalent molecule. Right. Now, ion-induced dipole. Okay, what is an ion-induced dipole? This is an attraction caused by an ion creating a temporary dipole in a non-polar substance. Okay, so our non-polar substance, let's say in this case it could be oil of some sort. Okay, if I put a polar substance like, again, NaCl, and I put into a non-polar substance, I said an oil, but I'm trying to think of one that might be better for us. In fact, let me just go with oil. I'm not going to give you the chemical formula for it because there's lots of different ones, but what I want to show you is this. An oil molecule, if I was to draw it, is going to have an electron cloud like that, which means that it has an even distribution. There's no one side that is, okay? There's no one side that is positive or one side that is negative. So if I bring these two into contact with that particular substance, okay, what's going to happen is that it's going to cause a temporary dipole. So depending on which one comes into contact, let's say the chlorine comes into contact, what it's going to do, because it's negative, it is going to send the electrons towards the back of the molecule, and it's going to make that side slightly negative, leaving the front slightly positive. But that's only for the split second or the instantaneous time that these two are anywhere near the oil. The second they move, as soon as they move away, okay, all of this comes back and it goes back to being neutral. Okay, so it's instantaneous and it doesn't last very long. It is temporary. Now, what about a dipole-induced dipole? Exactly the same idea as our ion dipole, except this time you're going to have a polar substance and then you're going to have a non-polar substance. Okay, so an example again could be oil and water. If you put oil into water, if I put water at the bottom, I'm then going to find that I'm going to have a layer of oil on the top. They aren't going to mix. But between the two layers, there's going to be this temporary, there's going to be a temporary attraction. So that it'll keep the layers together right up until the time that I pour it or shake it or get it to do something, okay? So the dipole-induced dipole, dipole substance or a polar substance and a non-polar substance, our example is oil and water. Then the last one of these forces is our instantaneous dipole, an induced dipole, or sometimes it's known as a London force. And these are temporary forces. If I can get my pen to work, there we go. Temporary forces between non-polar molecules. So in other words, it is what makes oil stick together in an oil droplet. Okay, it's the thing that keeps substances together in their droplets, especially if they are non-polar. Okay, they are really, really, really weak forces. And if I have a look at the different examples that we've got here, a dipole-dipole, an ion-dipole, an ion-induced dipole, a dipole-induced dipole, and an instantaneous dipole. These are all particularly weak forces of attraction. Okay, they are not very strong. Some can be stronger than others. Okay, we can have some of these stronger than others, but in general, they're all weak. The weakest, like I said, some can be stronger than others. The weakest here is our induced dipole or our London forces. These are our weakest intermolecular forces, IMF, intermolecular forces. Okay. I said to you, if you remember correctly and you've been tracking with what I've been saying, because guys, we're hitting theory hard today. There's a lot of theory. So I know that you're trying to just catch up and keep pace. Don't worry, you'll get there. Okay, you'll catch up. It's all good. Okay, but if you've been paying attention and something in your brain's going, hang on, she said there were 6. You're 100% correct. I did say there were 6, but we've discussed 5 so far. The 5 that we've discussed are the weakest, okay? There is one more called hydrogen bonding that we're going to talk about. And hydrogen bonding sits, in terms of strength, it sits between the weak ones, our dipoles, our induced dipoles, all of those, and our intramolecular bonding. So it sits between ionic and covalent bonding and these intermolecular forces that we've just discussed. So it sits somewhere. It's not quite up at the top with our bonding, and it's not quite as weak as these ones are. So it's the strongest of our intermolecular forces, and it's known as hydrogen bonding. Okay, so that's the next one that we will talk about. Now, what have I got for you here? This is just a way of helping you to figure out what we're dealing with, because there's 6 forces, and yes, I haven't gone into detail with hydrogen bonding yet for a reason, okay? But how do we know what the forces are? So this is a good way to just check yourself, okay? So ask yourself a few questions. If you're given a molecule, you'll be given a question like I've got for you at the end of this section or at the end of this lesson. You then can ask yourself a few questions. Okay, first one, are ions involved? So if there are ions involved, and we say yes, we're going to go in this direction. Then there's 2 options. It's either going to be an ion dipole force, or it's going to be an ion-induced dipole. Okay, here it says ionic bonding. So ion dipole, or I'm going to say ion-induced. I'm going to add that one in here. Okay, if it's no, this board definitely doesn't like me today. It keeps jumping all over the place. If it's no, okay, now we're going to ask ourselves the question, are there polar molecules? Okay, yes or no? If the answer is yes, what options do we have for polar molecules? We've got dipole forces, and we've also got dipole-induced forces. Okay. The other example is hydrogen bonding, which we haven't spoken about yet, and we will talk about now, but that is our other possibility if there are polar molecules. If your answer is no, there aren't any polar molecules, then the only possible option could be London forces. Okay. Now I want you to stop and think for a minute. I don't expect you to quickly write down all this thing of what I've got on the, I don't need you to do that. This is just an example of how to think through this section. Ask yourself a question. Molecules, ions. Are there ions involved? Yes? Okay, what are the possibilities when there are ions involved? There's ion dipole and there's ion-induced dipole. So those are the only 2 forces we could possibly have. If the answer is no ions, then we ask ourselves one more question. Okay, so no ions, just molecules. Are they polar or are they non-polar? Okay, if they're polar, what can we have? We can have dipole-dipole, and we can have dipole-induced dipole. Okay, so we can have those 2. And then the third one that we're going to talk about is going to be hydrogen bonding. But so far, we've got dipole-dipole and dipole-induced. Okay, so remember I said to you, ions, it's going to be ion dipole or ion induced. No ions, just molecules, it's dipole dipole or dipole induced. So far, we've got 4 out of the 5. So the only other possibilities, if we say no, the molecules are not polar, the only thing left has to be our London forces. Okay, so it's just a method of thinking through. If it works for you, awesome. It's one way to use. If it doesn't work for you, that's cool. There's no problem with that. I know that you're going to figure out a way to choose the right answers for these questions, okay, or whatever question you are faced with. Okay, so looking at this, these are the types of questions that we have. If the given pairs of substances in the table below were mixed together, list the intermolecular forces that would be involved. Okay, now I'm going to do the first one with you. Okay, we haven't done hydrogen bonding yet, so we're just going to work with the 6 that we've got. And I'm going to write them down just quickly. and it's going to be dipole, dipole, and it's going to be induced dipole, and it's going to be ion dipole, and it's going to be ion induced dipole, and it's going to be London forces. Okay, now we're going to go for another break, but what I need you to do is I need you to have a quick look for your periodic table. Hopefully you've got a periodic table with you, or there's one in the classroom or one in the textbook, because we're going to need it after the break. Okay, so have a quick look for a periodic table. We're going to go for an ad break, and then when we come back from the break, I'm going to need you to be working with your periodic table so that we can answer these questions together. Okay, so off you go, have a break. See you shortly. Welcome back from your break, everyone, and let's get back to the questions that I left you with. I'm going to do one example with you just to show you. I know I've got a whole lot, but I'm just doing one example with you because I want to get onto hydrogen bonding. It's really important that we cover that. So have a look at what I've got on the board, and then we'll work through it together. Okay, so type of intermolecular force, I'm going to use the second one of Mg2 plus and H2O. Okay, your Mg2 plus is an ion. Okay, remember we will ask ourselves the questions, are there ions? Yes or no? Yes, there's an ion. So what sort of force should we expect? We should definitely expect an ion induced, okay? But now I just want to double check what's happening with this H2O, right? For that, you need to have your periodic table. Except when the board decides it's going to jump all over me. Sorry, guys and girls. Apparently, we've got gremlins in the board today. Got no idea where my page has just gone. But it looks like the page has just disappeared. Okay, anyway, what I wanted to show you was find this and see if, there we go. Have a look. We've got oxygen with a value of 3.5, and we've got hydrogen with a value of 2.1. That means that our electronegativity difference is 3.5 minus 2.1, which is going to give us a difference of 1.4. Okay, that's a very polar substance, right? So if we have a look at what our original question was, it was Mg2 plus and it was H2O. So you're now going to end up with an Mg2 plus. You're going to have ion induced, possibly or definitely ion. And then what do we have with our other substance? We have a dipole. So what we've got now is an ion dipole intermolecular forces. So not ion induced. Okay, that was a possibility. But because there's an ion and there's a dipole, the intermolecular force we've got now is an ion dipole. Okay, so let's go back to what we were working on and move on. I want you to have a look at these. Okay, again, just a summary for you. It's a definition of what London dispersion forces are, what dipole forces are, and what hydrogen bonding is. Okay, so let's talk about this hydrogen bonding. It says here it's an attraction between molecules with NH, OH, and FH bonds. It is extremely polar. They're very strong dipole-dipole forces. And here you've got diagrams where you've got, maybe guys use a pink one. These are two non-polar substances. Over here you've got a big one and a small one. So these are definitely polar substances. And here you've got an unusual shape, and remember this is water, so it's angular or bent. And there you've got an indication that there could possibly be a stronger form of attraction. So what do hydrogen bonds actually consist of, or what are they really? Now, I can't find where the rest of the information's gone, so I'm just going to have to tell you here. Okay, they are our strongest bonds. All right, they are definitely our strongest bonds, or should I say our strongest forces. Okay, remember that even though it has got the word bonding in it, it is not a true bond. It is just a really strong force of attraction. Okay, our London dispersion forces are our weakest. Okay, and then all of our dipole forces, our dipole or our induced dipoles, they sit here in the middle between the two of them. Okay, so you can see we've got a column here for relative strength. We've got the weakest, with hydrogen bonding being the weakest. We've got our medium strength being our dipole, and then the strongest being the hydrogen. Okay. Now, other things that we need to know, and I want to talk to you about the hydrogen bonds in particular. Okay, so I'm going to add this to the page. All right. Our hydrogen bonds. Okay, I'm just going to call them H bonds. It should be hydrogen bonding. Okay. They occur between atoms with a high electronegativity okay, atoms with a high electronegativity and hydrogen. All right, and you will see here it said to us NH, OH, and FH. So I want you to go and have a look at the periodic table again. Let's go and look at our periodic table. And let's have a look at these substances that we're talking about. NH, OH, and FH. Okay. Here is nitrogen. There is oxygen. And there is fluorine. Okay. These three substances have got electronegativities of 3, 3.5, and 4. Have a look at our hydrogen over here on this side. Hydrogen is a tiny little atom, and its electronegativity is fairly high. It's 2.1. But the important piece of information here is if you go 3 minus 2.1, we're going to get 0.9. It's fairly high. 3.5 minus 2.1, we're going to get 1.4. It's getting stronger. 4 minus 2.1 is going to give us 1.9. And my maths is definitely in need of help today. 1.9. Okay? This difference is getting bigger as we move across the table. Fluorine is our most electronegative element. And this is what makes hydrogen bonding so special. Hydrogen, because a hydrogen is always involved. And the second part of it is that it has to be the three most electronegative elements. And they are going to be nitrogen, fluorine, and oxygen. Okay, now it can occur with others, right? And that's quite unusual. But our three most common are nitrogen, fluorine, and oxygen. That being the case, which substances are you likely to find hydrogen bonding in? You're definitely going to find it in ammonia. Okay? You are certainly going to find it in water, and you will also find it in hydrogen fluoride. Okay, so hydrogen bonding, even though it is incorrectly or inaccurately, put it that way, it's inaccurately named, okay? It is our strongest intermolecular force. Remember, IMF is intermolecular force, okay? With our London forces being our weakest. So let's have a look at a sort of question that you can expect to answer in a section like this. Okay, now look here. Talking about hydrogen bonding. A hydride is anything that bonds to a hydrogen. Okay, so what we've got are melting points over here and boiling points over there. And what I want you to have a look at is look at the trend. So in other words, the pattern. Look here, starts up there, it dips, and it increases. Okay, ammonia starts, dips, starts to increase. Hydrogen fluorides dips, starts to increase. The carbon, it just increases from the beginning. Okay, what does that mean? Because carbon seems to follow one pattern, the others follow a different pattern. Let's have a look at our periodic table again. Okay, so fluorine is going to be at the top of our group. And if we go down here, fluorine, chlorine, bromine, iodine, what happens is fluorine's got a high bond, a high boiling point or melting point, but then chlorine dips, bromine dips. H2O, a high boiling point, but H2S, it dips. NH3, high, but pH3, it dips. But C, Si, Ge, there is no dip. Okay, so this last one, there is a consistent trend. So what that is showing us, here is our H2O at the top of the one group, our NH3 at the top of the other, and our HF. Those three substances have got different, they are different to the pattern because of their hydrogen bonding. Okay, so that is what happens with their melting point. What about with their boiling points? Okay, exactly the same thing. Here's our carbon going to silicon, go to germanium, going to tin. Nice, steady increase. Look at our water. High, H2S. Low, H2SE. Getting a little bit higher, H2TE. Getting higher. What about our HF? High, drops to HCl. That's not the one I wanted. White is not a good color here. HF drops to HCl, ASH3, SPH3 starts to increase again. And our last one, okay, NH3, it's high. So again, these three substances are unusual in their behavior because of their hydrogen bonding. Everything else, all of these, have got a pattern because of their intermolecular forces. Okay? Their intermolecular forces are the weaker ones. They are the van der Waals forces, the dipole-dipole, the dipole-induced. Exactly the same here. They follow a pattern that as the molecule gets bigger, all right, as the mass gets bigger, their boiling point and their melting point gets bigger. Now, a typical question that you can get asked is from the graphs, three substances seem to be completely out of character. Which substances are they? What are the electronegativity values of the three elements bonded with H? Which elements have a higher electronegativity than these three elements? And what is the size of the atoms of each of these elements compared with the others in each respective group? Okay, so let's talk about these. What are the three substances that are completely out of character? Which substances are they? We're going to say they are H2O. We're going to say it's NH3 and it is HF. Okay. What are the electronegativity values of the three? Remember, we had a look at our periodic table. We'll zip across quickly and have a look at it now. Okay. They are 3, 3.5, and 4. So 3, 3.5, and 4. And in fact, I want to make a change here. These are the substances, these are the molecules, but what are the atoms? I want to write here that the atoms are oxygen, the atom concerned here is nitrogen, and the atom concerned here is fluorine. Okay? So 3 for oxygen, 3.5 for nitrogen, and 4 for fluorine. Which elements have a higher electronegativity than these three elements? There are none. There are no elements with a higher electronegativity. Okay? These three have the highest electronegativity on our periodic table. And lastly, it says, what is the size of each of these elements compared with the others in each respective group? And this is where I want you to have a look at the periodic table again. And this is why periodic table is so important in chemistry especially, because it tells us so much about the substances. Let's just have a look at the mass. So nitrogen has got a mass of 14. Phosphorus is 31. Astatine, or should I say arsenic, is 75. Okay, strontium. It's not strontium. My brain is getting confused here. 122. Bismuth, 209. Okay, what is happening? Each of these is getting bigger. Same thing with oxygen. 16, 32, 79, 128. Fluorine, 19, 35.5, 8. What's happening? The mass is increasing as we're going down. Okay? What does that tell you about the size of each atom? That means that the atom is getting bigger. So what is the size of atoms of each of these elements compared with the others in each respective group? They are the smallest atom in their group. Okay, now what does that mean in terms of the trend? Have a look here. Look what I've got. The smallest three atoms, your oxygen, your fluorine, and your nitrogen, have got higher boiling points than your biggest ones that are sitting over here. So the trend should be that when you increase molecular mass, or you increase the size, your melting point is going to increase. And the reason is because there are more intermolecular forces. But the exception, except nitrogen, oxygen, and fluorine. Okay, let's have a look what else I've got for you. Okay, so here's our clean graph. So let's just quickly recap. Our three smallest ones have got higher boiling points than our heaviest ones over here. Our three smallest elements per group have got higher melting points than the heaviest ones in their group. Okay? The trend is that as we go up, okay, as the mass increases, our intermolecular forces increase, except for the three that are involved in hydrogen bonding. So now, questions that you can answer on your own. State three types of intermolecular forces. How does the strength of hydrogen bonds compare with covalent or van der Waals? Why does hydrogen bonding not occur in HCl? What type of bonding does occur in HCl? You can see there is so much in this section, and it affects so much. It affects bonding, it affects behavior, it affects just how the atom itself operates. Okay, so we've done a lot of theory work, and well done for keeping up today. We've done a lot, and I've talked a lot, and I'm sure your ears are just ringing because we've done so much. Well done for keeping up. Well done for working so hard. And I look forward to seeing you next lesson, where we're going to carry on with physical science, grade 11. Bye.